Simultaneous One-Dimensional Random Walks by Lori Ballstad and Jesse Gassel. In this project, we will consider two simultaneous one-dimensional random walks which cannot cross, but they can collide. First, we want to think about how long it takes for a collision to occur, and then we want to consider how many collisions occur over a certain number of steps. We'll look at two main variables, the starting distance between the two walks and the amount of space over which the two can move, so the domain of the walk. Finally, we'll add an extension considering a rudimentary implementation of virus transmission between the 2 points and how transmission changes with increased social distancing. Here's the code that we build to make the random walk. We start with a for loop and have a bunch of if and elif and else statements, and we limit the range of the walk by preventing the points from going past a certain point. And when there's a collision, we have a little key, and it says to send them back to their pre-collision state and remove the collision from the list. So this means that we can't explicitly see collisions, but we know that they occur. The graph we see here is a walk for 100 steps, and we see that the points started close together, and the number 13 above the graph is the number of collisions that occurred in this one walk. We see that the walks don't actually touch because we're sending them back to the spot once they collide as a way to prevent crossing. Essentially, they collide and bounce back, but we don't show this explicitly. Now we'll take a look at what happens when the points start 1, really close together, 2, a medium distance apart, and 3, very far apart. The code for this part is basically the same as before, except we change the initial positions for each test that we run. So here are the 3 graphs from the different walks. We have the first graph on the left, which started about 2 units apart, had 13 collisions during that walk. And then in the middle, they started about 7 units apart and only had 2 collisions. And for the very last walk, which was about 19 units apart at the starting distance, didn't have any collisions at all. Now we take a look at the number of steps until we reach a collision in the walk. To do this, we create a function called firstCall, and that tracks when the first collision occurs in the walk. And we use a while loop instead of a for loop to make sure that it doesn't go on forever. We made a plot that tracked the starting distance between the points and how many steps it took to take until a collision occurred. In this graph, we see that on the x-axis, we have the distance starting apart, and the y-axis is the number of steps until a collision. And we see a linear step pattern, which means that the farther apart the points are, the more steps it takes for a collision to occur, which makes sense. For this next section, we fix the number of steps the walk will take, and then ask how many collisions occur during that time. We make a function that will count the number of collisions in a given number of steps, numCall. First, we ask how does the starting distance between the 2 points affect the number of collisions that occur? We see from the graph that when the starting points are further apart, then there are fewer collisions, in a decreasing exponential pattern. Again, this makes sense, though it is perhaps unexpected that the pattern is a decreasing exponential. This could arise from the increasing time it takes for the points to initially collide. Next, we ask how does the possible domain affect the number of collisions? When points have more space to travel over, we see a decrease in an exponential pattern again. We can see that larger and larger domains mean less and less collision, which is a sharper decrease than just moving the starting points apart. This is likely because there are more places for the points to occupy, so the points are less likely to get close together. Finally, we want to ask how the number of steps affects the number of collisions. We see from the graph that when we let the points walk for longer, we get more collisions in a near linear pattern, but this is expected. Finally, we consider a basic model of viral transmission. In this section, we want to think about one of the 2 points as being a carrier for a virus. When the points collide, the carrier point can transmit the virus or not, depending on how transmittable the virus is. This is a basic simulation of how practicing social distancing techniques in the COVID era could help flatten the curve and prevent the spread of the virus. We have 2 points, one who has the virus and the other who doesn't. To do this, we make a function that will count the number of collisions until transmission, the function named transmit, and this function includes the probability of transmission if they collide. The key in this code includes the variable rho, which is a random number between 0 and 1, and if rho is less than or equal to the probability of transmission, then we say a collision occurred, and we break the loop. In this function, the points can collide, but they won't always transmit the virus between them. In this first graph, we can see that a higher probability of transmission results in less collisions needed for transmission to occur. which makes sense. Next, we ask, how does the transmission probability affect the number of steps that occur until we get one transmission? This graph shows that when the transmission probability is very low, it takes a lot of steps, around 200, for transmission to actually occur. And then when we have a very high transmission probability, there aren't that many steps needed until we get the first transmission. Then we add some sort of social distance or mask-wearing measure meant to limit contact between the 2 points. We do this by making a new function, transmit2, and letting them walk, and then when they collide, asking if they can actually collide, because we say they break the distance with probability close, which is a new input in the function, and then asking if transmission occurs as before. We can see that less transmissible viruses take more steps to transmit, and less contact leads to more steps to transmission. Remember, we can't control how transmissible a virus is, but we can control our distancing. We can see here how distancing can be a powerful way to limit virus transmission. Of course, this is a super simple model and doesn't consider a variety of important factors to public health. Some limitations we found was the lack of explicit collision in our functions, which is especially noticeable in the counting collisions exercises. While the function still works, it cannot explicitly show the collisions since we delete the point of collision. A second limitation is the simplicity of the transmission function, though it does show the power of social distancing and following the guidelines of the CDC. This project shows that points that start farther apart take longer to collide, and a larger domain results in fewer collisions. We can also see that, as expected, more steps lead to more collisions. Finally, our simple transmission model shows that viruses with higher transmission probabilities need fewer collisions and fewer steps to transmit. Adding limitations on transmission, like decreased contact, further decreases transmission, often quite severely. One of the most obvious extensions would be to turn the simulation into a 2D walk or simulate 2 or more points that are taking a simultaneous walk.